Okay, today we will videotape. I hope my iPhone is working. The SFU will, anyway, audio recording my lectures. I put it to the canvas so that for the missing, those not coming to the lectures can see it. So last time, we mainly telling you what's the definitions of derivatives. It's a fairly basic objects. Basically, it's the rate of change that we usually compute when we study a graph, a straight line, the slope of a tangent, etc. So if you give me a function y to the f of x, if you give me a point, so like this. So in general, your curve, your graph will be very nice, no jump, no sharp points, or smooth. So if this is A here, then what the f pi A is defined to be this limit. So it's very important to remember the definitions. The limits of this different quotient. And this quotient is precisely your slope when computed a straight line, the line segment secant. You have the rise over the run. So, and then you take the limits, then you get a tangent, which is precisely touch it. This is a tangent. So the tangent is straight line, so you have a slope, and the slope of the tangent will be your derivatives. And it will be equal to this limit. So that computes. And this limits may exist or may not exist, depending on situations. Later we'll see when you don't have, not exist, then you actually can tell the function is smooth or not. Okay, so this basically I review what I do last time. Okay, there's one slide we didn't cover last time is this notation. Okay, so this is the Wednesday, still the Wednesday that you know, we're missing some of the page. Okay, as I said, the complete looks already put it on the canvas. Okay, so usually the derivatives, the notations, we're using pi, f pi. You give me the functions f of x, so you have f pi. Now, depending on the situation, sometimes I'm using another notation which is more convenient. So just different notation is just more convenient for us. F pi is a very useful notation, especially the f is given. Because you sometimes you say y equal to f of x, this is your graph. So y will be correspond the functional values. So sometimes I will also write y pi to represent the derivatives. Okay, you read as a y pi or the derivative of y. Okay, now this notation is very short, but there's a not convenient. Is because I didn't say express the y pi. Actually, I have two variables, x and y. I didn't show the x. So sometimes, if the functions have more than one variables, or you have to specify the variables x, so I use dy dx. Okay, so this is also a very common notation. As a fraction, okay, with dy dx seems like a fractions, but now it's just a notation. You cannot separate them. It has a one symbol, dy over dx. But later we'll actually prove some of the properties or some application. This actually can be looked at as a fraction. So this notation actually has some meaning. So dy dx, or some other variant, say you can always replace your y by f, df dx. Okay. Sometimes you will also write f of x So specify functions x. So df of x dx. Okay. Well, that you can put it here or you can put it out here. So let me write in this one. That means it's write as a fraction. So df of x over dx. So it's slightly things. The notation, as I mentioned, so the fractions actually is as a whole. So you shouldn't regard as fractions. So d over dx actually is a special notation. It's called the differential operator. Okay. And dy dx is Leibniz notation. You probably only know this calculus is invented by Newton, but at the same time, in fact, there's Leibniz also about the same time invented. The notation we use is not the Newton notation. Newton notation is actually capital D, dy, say dx like this. So this is a Newton old fraction notation we seldom use because this have some disadvantage. This is Leibniz is also another person, just two people, Newton and Leibniz, invented the similar theory of calculus about the same time. Okay. Okay, so this notation. So basically, mostly I will use a f pi of x and sometimes dy dx. So these are the two most common notation we use. Okay. We do this last time. Let me do one more example. So remember that the derivatives is when we finding a tangent. So therefore, the first application is using derivatives finding the tangent for given a curve. So a tangent line of a curve, of course, we only consider a curve, a straight line. The tangent is itself. So tangent line passing through the point. So the slope is precisely equal to the derivatives, the m. Okay. So you find me the derivatives, then we have the slope of the tangent. So here we think the point x is opposed to a. Opposed to the point a. Okay, you see the x opposed to a. So, or if you have a graph here, so this is a. You're actually finding this tangent, and your x is actually opposed to a. Okay, or you can actually think the rate of change. So this is the distance when x approach zeros. X approach a, that means is when the distance between x and a will be 10 to zeros. So in other words, so that means delta x, the distance between them, 10 to zeros. Okay? They will be the same limits. No matter x tend to a or delta x tend to zeros, I'm just changing the variables. They are the same limits. Okay, so therefore now, provided that the derivatives are already defined out, the derivatives, you understand this is the limit, and you compute it, then now it's quite easy to write down the formula of tangent, which is I'm using point slope form, an equation passing through a point with a slope. So which is y minus f of x, because I'm passing through the point a f of a, and the slope m, which should be my derivatives, multiplied as x minus a. Okay, this is if you recall, this is called the point slope form of the equation. If you're passing to passing through x naught, y naught, and the slope is m, then the equation, if you remember that, you must learn in high school like this. So this is point slope form. So I'm particularly applying my tangent. Okay? So now any curve, any functions, finding a tangent becomes quite standard or office, just computing the derivatives. Once you know the derivatives, you know the tangent. Okay? So if you know the tangent, then the functions will look like the tangent. So possibly you will tell more about the graph of functions. So let me give one example. So it's a very typical question. Almost the first problem we want to solve by using the calculus, finding the tangent. So how to determine an equation of tangent to the curve? Now I'm using a fairly simple curve. This curve, of course, is the inversions of the x squared, so it must be like this. Okay, I know that it's a continuous, so simple functions. Actually have no sharp point, later we'll explain. So passing through 1 minus 1, this point is 1 minus 1. Okay, so I actually want to find out is the equations of the tangent. So you see that this is certainly you expect a tangent here. This is a tangent. Okay? Before the calculus, you don't have a very good method to find a tangent. Okay? So this kind, the right hand side is actually geometry, how to draw tangent. Now I can, because the function is given explicitly, I can now, using algebra, to find out the slope of the tangent, which is the derivatives. So this one is actually derivatives. Now, because of my a, I'm computing a particular point when a equals 1. So this slope, in fact, is my f pi of 1. Because a is 1. Okay, a is 1 here. Okay? So you have this limits. You can, using another form, the delta x tends to 0, you will have the same calculations. So by definitions, my derivatives or the slope is equal to this limits. Okay? I need to compute this limits by definition. So my functions f of x is given to be this. This is my first term, minus f of 1. F of 1 is already given because this point is 1 f of 1. Right? The point in the graph is x f of x. So therefore the f1, you can either substitute back or it's given to be minus 1 over x minus 1. So once you have the definitions, you plug in your functions and you get this limits. And now you simplify it. Okay, so let me put one more step here. So minus x plus 1, x minus over 1. So this is the limits you want to compute. As I mentioned last time, when you substitute, you always get 0 over 0. So you need to do some work to compute these different derivatives. This is a very simple limit. You need is to factor it. So let me factor it in the forms like this. Okay. So usually we factor x minus 1, x plus 1 is x squared minus 1. So I take out the negative side. So therefore, you cancel the term. Then now you have the limits, x tend to 1, x plus 1. Okay. Then now you can substitute 1 into the limits because you cancel the term to make it 0 so already. So you get negative 2. Okay. So a very simple calculation of the limits. I know that the derivatives of f pi of 1 is actually minus 2. Well, that agrees the geometry here, so the slope is minus 2, right? On this side is a negative slope. And actually, I know the degree. You can use a calculator. This angle is a tangent theta. You're using arctangent, and you compute the angle. So besides, you know the geometry. So the slope is minus 2. Just compute. and part